Recording is on. So welcome to CE305 Unit 4 lecture. So this is the module on languages and compiler, or as I like to call it, the module on how to build your own compiler. Today's lecture is on finite automata and regular expression. By the way, can everyone again confirm that they can see the slides, like the presentation on their screen properly? Thank you so much for confirming. Okay, as usual, the lecture slides are already available on Moodle. So let's get started. You can download the lecture slides directly from Moodle just in case you want to have a reference. So today, we are going to cover an important topic in theoretical sense. So let's look into the history. We have a field of study called computability theory, which was really popular as a research topic back in the 1930s and 1950s. Now, the goal of computability theory is to understand what is computable by a machine or what is not computable. Today, this field of study is not pursued that much anymore because the majority of the research question that they had back then has been answered, but it has laid out some foundation for a very important field that we are going to deal with, or we are going to learn today. Now, when I say in computability theory, the goal is that what a machine can compute or not compute. Let's take an example. Let's say you are developing a specification of a sorting algorithm. So how do you know that the program that you have written for the sorting algorithm matches the specification? So you will have another program to verify whether it meets the specification of that sorting algorithm or not. So that is part of the computability theory. Now, the computability theory led to the development of models of computation, or the field of finite automata. Now, automata or automaton is another word for machine. So finite automata is an abstract model of a computing machine with limited resources such as memory. Let's take an example. So let's say here we have a finite automata, which can be thought as a representation of an abstract computing machine. So imagine this is a simple, very simple computer, but an abstract model of that. And we call this finite automata as M1. So if you should have already done finite automata before, if you haven't, we will be going through it again today, just to jog your memory. So the M1, this finite automata, has a few states. The states here are the one which is in circles here. So we have the states Q1, Q2, and Q3. Now, as you can see, these states are related to each other through the curved lines. These lines are called the transition. Now, by transition, we mean that a machine changes the state from Q1 to Q2 through the transition, which is 1 here. So these are called the transition. Now, in a machine, we have a starting state, which we denote by a circle and an arrow pointing to it. And we have an accept state, which is denoted by like two circles converging on each other. So given these are the thing, let's say that this finite automata is able to accept input as only finite string. We do not deal with infinite string. In theory or mathematical perspective, we can have that, but in case of real machines, we only deal with finite strings or finite input strings. So the goal is that given we have like a finite string as input, the output needs to be whether this machine can accept that string or reject that string, which means whether the machine can read that string or it cannot. So the computation process for this machine to happen, step one is you begin at the start state, which is in this machine, it is the Q1. And then you read the input symbol that comes in. And next step is follow the corresponding transition of these states. So from Q1 to Q2 to Q3, or any of the transition in between. And depending on that, if the final string, if it ends up in the accept state, then the input string is accepted. If it does not, then it rejects it. So for this finite automata, let's take an example of the string 01101. So when we start with the Q1, the start state, if it is 0, so here we can see that Q1 can go to itself if it is 0, or if it is 1, then it moves to the next state, which is Q2. So if it is 0, it comes back to itself. So it remains in the same state. Next is the 1 of the input string. So if it is 1, because it's in the same state here, now because it's 1, it moves to the next state, which is Q2. The next is 1 of the input from the input string. So again, from Q2, if it is 1, it can move to the Q3, which is the next state again. So that is absolutely correct. So now from Q2, we move to Q3. And then we have 0, which is if it is on Q3, it can move onto itself, like remain in the same state if it is 0 or 1. So for 0 and 1, again, the final state is the accept state for this particular input string. So we know that this input string 01101 is accepted because the final, the 1 of the whole input string remains in the accept state. So this machine will accept the string 01101. Let's take another example. If the input string now changes to 00101, so 0 means we start from the Q1 again, the start state. And because it is 0, we remain on the Q1 because it transitioned to itself. The next is 0, it again remains to itself on the same state because it again transitions to itself. Then we have the 1, which is now the Q1 changes state, like the state changes to Q2. Then we have 0. Now Q2 has, if it is 0, the machine changes the state from Q2 to Q1. And the end is the 1 again. So Q1 then moves, like the machine moves the state from Q1 to Q2. But as you can see, the end Q2 is not the accept state. So the machine will actually reject this string. Another pattern that you can see, that this machine, in order to accept any string, it has a commonality. That common thing is if a substring contains 1 1, then only like this machine M1 will accept that string. So by that meaning, it means that M1 accepts exactly those string in A. A here, let's call it a language, which is a set of strings. So M1 will accept the language A if the A contains substring 1 1. So this machine will only be valid for that language. Or mathematically, we can also like denote it like this, that A is the language of M1, or A equals L M1, which means that the language A belongs to the is accepted by the machine M1. So, so far, does this make sense? Saukanya has asked, in the second example, will it reject the string because it never reaches Q3? Yes, Saukanya, that is correct. It's because here, as you can see, the Q3 is the accept state. If the end of the string, input string that is provided to the machine, if by the end of the input string, it does not reaches the accept state, which is Q3 in this case, then it will reject that string. So that string won't belong to the language which is accepted by M1. So now that we know this, so finite automata basically comes in two variants. One is deterministic finite automata, and another one is non-deterministic finite automata. And we will be exploring these in today's lecture. And now let's take a step back to realize that why we need finite automata in languages and compiler. So it's very important in this step of lexical analysis. When we specify the lexical structure using regular expressions, which we have already learned in the previous lecture. So after the lexical structure is specified using regular expression, tokenization can be implemented using finite state automata. And it comes in two forms: deterministic finite automata, or DFA, and non-deterministic finite automata, or NFA. Now, the implementation is something like this. So you come up with the regular expression. Regular expression then determines or creates the non-deterministic finite automata. Then non-deterministic finite automata is processed further to create the deterministic finite automata. And from the deterministic finite automata, when you know the states and the inputs, then you can generate table-driven tokenization. So in this way, once from the DFA, you have created the table of states and transition, it is easier for to create the tokens, or tokenization happens based on that. So as we have already discussed with the previous example, we have the machines, or finite automata has the states, which are denoted by circles. State can be you can denote it as like S, Q, in whichever way you would like to denote it. The initial state, or the start state, is denoted by a circle, the state's name, and it has an arrow in the beginning. The accepting state is again denoted by double circles and the state's name. Now, when we mention transition, it means finite automata changes a state from one state to another, and that happens because of an input. Now, when that change in state happen, then we call it transition in finite automata. So here, if in the state S1, if we go from S1 to S2, then the input A is here is the reason for this transition to happen. Let's again take simple example to understand this. So this is an example of a very simplistic finite automata which accepts 1 as a string, which means imagine if 0 and 1 is the input signal in a computer machine. So where 0 is the current is not flowing or the switch is off, and 1 means the current is flowing. So this will represent that machine, that if the machine has current flowing or the input string is 1, then it moves to the state, accept state S2. So this is an example of such a machine. Another example is, let's say you have a finite automata that accepts a sequence of ones followed by a 0 over the alphabet 1 and 0, which means if you can recall, alphabets are the symbols that the language can like be made of, language is made of. So if the alphabets consist of 1 and 0, so this machine is accepts any sequence of string that consists of ones followed by a 0. Then only this machine, finite automata, will accept the string. Okay, we have a question. Let's have a look. Wouldn't automata 1 technically accept a sequence of zeros and then a 1? No, Soren, it would not. The reason being why it wouldn't accept a sequence of zeros, because in this simplistic machine, the one that I'm showing, you can see it doesn't have any transition that can accept 0. So here it is just, it's not defined. So this machine would not even accept like 0 as the like for the transition to happen to the accept state. So this machine does not accept any zeros, if that makes sense. Let me mark this question as answered. Okay, great. So let's look at a bit more complicated example, but again, like simple example to understand how the machines, finite automata work. Imagine that in your program or your machine can accept the keyword if. So this is an example of the machine that can accept the like string if. So as you can see, the state is 1 of that machine. It changes to state 2 if and only if the input string, the first one, is I. Now, after it changes the state to 2, if the next substring of the string, input string, is F, then only it will reach the accept state 3. So this is an example that can accept the keyword if. If you have a different digit, which is, let's say, X instead, then this machine will reject that keyword because that will be IX. But this machine accepts the keyword if. Now, that being said, let's look at another machine, which is here, like the finite automata for this one. Here, this one accepts like alphabet, which is like the A to Z, and also the next state, it will accept numbers and alphabet as well. So this machine will only work for that. So the start state, as you can see, it will move to the next state, which is also the accept state here. So if that will only happen if the input string starts with A to Z. And then the next portion of the input string, if it is either a number, which is 0 to 9, or an alphabet A to Z, then you can see this machine will accept any of those strings. Now, that being said, another thing to note is that this machine will also accept the keyword if as well. But if the machine, finite automata, if cannot accept the strings, all these strings for this one, ID. But the ID one can accept the one for keyword for if, because it can accept A to Z, any of the alphabets. Let's take another example of finite automata, which accepts only numbers or integers. So if you have the regular expression like this, then the finite automata could be shown in this way, where you start from the state 1, you move to the accept state 2, and that is all only accepted when you have the numbers 0 to 9, or the accept state can also have the numbers 0 to 9 as well. So this finite automata will accept any string that consists of integers or numbers. Let's take a bit more complicated example here of a finite automata. So this machine accepts the, like, let's say it has a start string SS. This machine changes the start state SS. This machine will only change the state to S1 if the transition is dependent on the input string 0. And then this machine will change the state S1 to either it will go back to state SS, or it will go to the accept state SE. It will go to accept state SE if the input string consists of the 0, or if the machine changes the state from S1 to SS. That will only happen if the input string is 1. Now, one thing you can see from here, that a valid string that can be accepted by this machine, that can only happen if the substring is actually consist of 0, 0, like consecutive zeros. So this machine accepts the string for which the substring has to be 0, 0. Now, we have someone mention something in the chat. Yes, Andre, you're absolutely correct. So subset or substring must be 0, 0 for the accept. That is correct. So this machine will accept the strings that consist of 0, 0 subsequently. Now, another thing to keep in mind, which is very important in finite automata, especially for non-finite deterministic automata, is the epsilon moves. So epsilon move is a type of transition where, let's say, the machine changes state from S1 to S2, but this is actually empty, which means that the epsilon transition is empty string, which means it doesn't consist of any string. So the machine changes state with no input. So we need to keep this in mind as well. Now, let's look at the differences between deterministic finite automata and non-deterministic finite automata for the sake of the, let's say, not saying a lot of word, we will be saying them as DFA and NFA. So in DFA, you have one of the important difference with the NFA is that in DFA, you have one transition input per state. Whereas for NFA, you can have multiple transition for one input in a given state. What do I mean by that? Let's go back here. As you can see, so here, although, yeah, this one is not really a great, but So state 1 here can go to state 2 based on 0, or state 1 can also remain here like on itself based on 1. So here we have multiple transitions for the same state. And when you compare with DFA can only have one particular transition. I will be showing better example later down so that it is more understandable. But anyhow, one of the key difference is DFA can only have one transition per input per state. But NFA will have multiple transition from one input in a given state. Another key difference between DFA and NFA is that DFA does not have epsilon moves, or it doesn't have the epsilon transitions, which is no input. Whereas NFA will have the epsilon moves or epsilon transition. So when we execute DFA and NFA, let's say for DFA, you can only take one path through the state graph. Whereas for NFA, you can choose whether to make epsilon moves or not. In DFA, the transitions completely determined by the input. Whereas in NFA, you can choose which transition to take for a single input when multiple transitions are available. And I will be showing them with examples shortly. Another thing in DFA, it accepts when it reaches an accept state. For NFA, it accepts if there is some trace for that input which it reaches an accept state. So, okay, this is a better example because the one I showed earlier, it actually didn't have multiple state with the same input. So as you can see, this is a perfect example of NFA. Because the start state that you can see for the finite automata, for this finite automata, is that for if 0 happens as the input string, then this machine can either remain in the same state S1, or it can also go to the next state, which is S2, because here the transition for 0 can happen in both ways. That's why you can see this has a multiple state. So this one is a very good example of NFA. And now, based on this finite automata, if we consider the input string as 1, 0, 0, you can say if we have 1 from the if we start from the start state, if we have 1, then it remains in the same state S1. Then the second is the 0 from the input string. So if it chooses to remain in the same state, then it will just stay in the same state. And the next 0, if it remains in the same state, it can remain here, or the machine can change the state to S2. But as you can see that 1, 0, 0 here, for this might not be a valid input string, because the transition that we took, it did not reach the S3. However, that being said, let's take another set of transitions where the machine, instead of remaining to itself, so it goes through 1, so it remains in the same state. The next one is 0. Instead of remaining in the same state, it moves to S2. And the next is 0. So from it changes the state again to S3. Now this is a valid string because it has reached the accept state. So as you can see, it kind of creates ambiguity in the transition when it comes to NFA, because NFA can have multiple state for the same input, which makes it difficult to understand the transition that or the path it should take in the graph in order to reach the final accept state. Now, there are few things in the chat. Let's see. So Saukarnya has asked, what determines which state should it choose if the input is 0? Now, it completely it depends on the machine itself. So it can be either or. There is no particular rule that if we have this particular example of NFA, there is no particular rule that how it should like choose which transition to happen. That being said, if the goal is to reach the accept state, then you can enforce that onto the NFA. But in order to make that, you can actually simplify the NFA to DFA so that the machine doesn't have any form of ambiguity when it comes to multiple state. And as I have mentioned, the key difference of DFA that it doesn't have multiple state for the same input. So if you can recall that from the regex or regular expression, first the NFA is generated. From the NFA, it is simplified to generate the DFA. And that is important because when the DFA is generated, there is no form of ambiguity in the transition because you do not have multiple state. So that will make it clear whether a string can be an accepted one or not, if that makes sense. So Dragos has asked, random or some probability, I guess. To be honest, yes. Like NFA is, again, like if you have multiple transition, like multiple state transition for the same input, it makes it difficult to understand, okay, which exact path to take to reach the final accept state. Now we can determine it because we can visually see the graph, but oftentimes it is difficult for the finite machine, finite automata to decide that. That's why converting from NFA to DFA is important. And we will be also looking into that shortly in this lecture as well. Now, assuming that NFAs and DFAs recognize the same set of languages, DFAs are easier to execute as there are no choices to consider, especially given multiple state transition. But for DFA, they can be exponentially larger than an equivalent NFA as well. So the state transition can be exponentially larger in some cases. NFAs can be more compact and simpler as multiple choices or state transition can be expressed more simply, but are more complex to execute directly when an input symbol like input string comes in and you have to reach the accept state. So let's take an example of the finite state. So this is the NFA and DFA, which accepts the input string as the regular expression, like it expressed by regular expression like this. So if you have the regular expression something like 1 or 0 and star and followed by 0 0 at the end, so this one will actually be accepted by both this NFA and DFA. But as you can see, given that here for the NFA, the start state, you have the multiple transition for 0 that it can either remain in the start state or go to the S2. It makes it difficult to reach the accept state in the NFA. Whereas the DFA, in this case, will make it very determined that it will reach the accept state if the valid input string following this regular expression is given as the input string for the DFA. So as I've mentioned that, notice that in the NFA, previous NFA, on 00, the input in can be still on S1, while on DFA, it reaches the accepting state. So what does equivalence mean here? So we will be dealing with equivalence, but let's go back to the example. So if it is 00, as you can see, one thing for sure, that if the input string ends with 00, it will reach the accept state for both NFA and the DFA. As you can see, like 0, so the state transition happens from S1 to S2 for 0, and the state transition again happens from S2 to S3, which is the accept state, for 0 again. So the substring 00, this will be an accept string. And for DFA, it's also the same as well. But here, when we say equivalent, that the input string can be equivalent for both NFA and DFA, so there must be some path labeled by the input string in question leading from the start state to the accepting state. Therefore, the equivalence here means all string that can be accepted by the NFA can also be reached by the equivalent DFA. So I hope that makes sense, that here equivalent means that from the start state, if in order to reach the accept state, there has to be the input string that is same even for the NFA and the DFA as well. For this case, it is the 00. Now, let's look at how you can convert regular expressions into the NFAs. Because if you can remember, in lexical analysis, the way that happens, that you have, so you have the lexical specification, from which you build the regular expression. From the regular expression, you then develop the NFA. Once you have the NFA, you further process it to create the DFA, so that there's no form of ambiguity like multiple state transition for the same input. And after the DFA is formed, from there you can do table-driven lexical analysis. So let's take at some of the example how we can do that. So you have the general form of a regular expression, let's call it M. So M has a start state with the accept state. That's it. Like, this is a very simplistic representation of regular expression to NFA if the regular expression is M. Then in the NFA, another important thing you can remember, that NFA has empty transitions or empty input, which is the epsilon moves, right? So you will denote that like this. And another thing to keep in mind is atomic regular when we say atomic regular expression, it means it only has one transition, and that transition is like A. If we call as the input as A, and it transits from the start state to the accept state in only one particular transition, then it's called the atomic regular expression, or the finite automata, or like NFA for that. Let's take an example of regular expression where you might have to concatenate A and B. So in this case, the finite automata like NFA will look something like, you have the A, then you make the epsilon move, and then the B reaches the accept state. So this is an NFA example for the regular expression, which is concatenation between like A and B. Another example of regular expression, which can be, let's say, it is A or B, then your NFA will look something like this, that you start with in the start state. The NFA then will have two epsilon moves, because it can either move to A or like move to A or B. So for that, then that's why we have created the epsilon move to A, or it can be for B. And this state can reach the accept state, again, like having epsilon moves as well. So this is another simplistic example of NFA for the regular expression A or B. Now, another thing to keep in mind is we have already seen that in regular expression, we use the star, which means it's kind of recurring to itself. So the state remains in itself for the input string, right? So we call that the clean star. And it is denoted, let's say the input string is A star. If we have to convert that to NFA, it will look something like this, where you have the start state. From there, you can make a transition if it is A, and then you reach the accept state. But because it is a star, like it recurs onto itself, you create another transition, which is epsilon move to back to the start state. So this is NFA's representation if you have a clean star, which is popularly used in regular expression. So keep this in mind, because we need to use these as the formula to create NFAs for a given regular expression. So let's consider this as an example. If you have the regular expression something like 1 or 0 star, then followed by 1, right? 1 has to be the accept state. Then the NFA will look something like this. So if you can remember, we are using this first. This rule where you have A or B. So your NFA will look something like the start transition and epsilon moves. Then it accepts A or B, and then it moves to the next state with epsilon. Using this formula, you can say for 1 or 0, we have done the same. So you start the epsilon move, and then again epsilon move to 1 or 0, and then to epsilon again. And now, because in the regular expression, we have used Klein star here on 1 or 0. So given the formula here, as we have mentioned, that the state next, like the final state here, recurs back using an epsilon move. We are doing the same here. So for G, which is for 1 or 0's next move, like next state, we are recurring back using an epsilon state. And then finally, we from G state, we move to the H state again, providing an epsilon move. And because at the end of the regular expression, we have 1, so we move from I to J, which now J is the accept state as the transition for 1. So as you can see, this NFA, like using the formulas that we have shown here for Klein star, concatenation on A and B, and A or B, using these formula, we have successfully developed NFA for the regular expression for this one. Now, so far, did it make sense? Any questions so far, by the way? So how many times, Sokanya has asked, how many times we need to go back where we have a star? So it's not about how many times, it's only one time. So you have to determine if, here's the thing, like let's say 1 or 0, right? 1 or 0 will lead, so the next state will be the state where it has to recur back to the start state. So as you can see here, 1 or 0, which like it reaches E and F, but E and F has to make the move to the next state based on the epsilon. So here the epsilon G is the next state for the 1 or 0, but because we have a star, from G we go back to the start state, which is the A. So this one here is like we are making the epsilon move based on this formula. So the goal of the epsilon is that it actually remains within the same state. But in NFA, because we can have epsilon moves, which is empty like transitions, for that one, we create, let's say, in-between state, which are the epsilon states. But because of the star, we go back to the start state. Now, given that we have the, so here, this example, where we have, this is the example of NFA for the regular expression 1 0 star followed by 1. If we have to now convert this to DFA, first remember that two things need to happen. DFA doesn't have multiple transition for the same input symbol. Another thing, it doesn't have epsilon moves. So we have to reduce this NFA in such a way that it doesn't consist any of the epsilon move or multiple state transition. And the way we do that, so you can see we have created a state S1 where we are actually consolidating the states A, B, C, D, H, I of the NFA. So A, B, C, D, H, I here are this one, A, B, C, D, H, and I. So we are consolidating all these states together into one state in the DFA. And then the next state that we determine is the S2, where within the S2, we are consolidating F, G, H, I, A, B, C, D. So if we go back, so F, G, H, I will be F, G, H, I, A, B, C, and D. So we are, let's imagine that these state, we are putting them together to create one state where, so that we do not have to make any epsilon move nor have multiple transition. So that's how here we are consolidating each of the state from the NFA to create new state for the DFA, so that we do not again have any epsilon moves or any multiple state. So you will see this DFA accepts the same regular expression as well as the NFA did. But another thing to note is that because of this, this one is a far more compact finite automata than the NFA that we have created. So if in real example, if you're given an NFA, what you have to do, closely look that how you can consolidate the states together in order to remove any epsilon moves or any form of multiple state transition. So in effect, we proceed by simulating multiple token execution model of the NFA. So each state of DFA corresponds to a non-empty substrate of the states of the NFA. The states correspond to the multiple state in which the NFA may be after a given input sequence. You also need to note that the number of state in the NFA might be much larger than the DFA, especially because it has epsilon moves as well. We make a DFA from the NFA such that each set of NFA states corresponds to the one DFA state. Since the NFA has a finite number of n states, DFA will have a finite number of state which can be determined by the formula that in DFA you have 2 to the power n minus 1 states compared to the NFA. So that's how we can mathematically like correlate DFA and NFA when it comes to number of states. So the basic, let's say, algorithm in order to kind of convert NFA to DFA, you have the start state of the DFA corresponding to the start state of the NFA, and all these states reachable through epsilon moves. We can add a transition from S to S hash to the DFA if S hash corresponds to the collections of the states in the NFA reachable from any of these states in the NFA corresponding to S on the input symbol A, including epsilon moves. So pause for a minute and think about what I just said. So here, the transition, if in the DFA, that if we consider that S transition happens to S from S to S hash, that can happen if S hash corresponds to the collection of states in the NFA reachable from any of these states in the NFA corresponding to S on the input symbol A. And we continue until we have captured all the permutations of the state and transitions of the NFA in the DFA. So this is how we can convert NFA to DFA. Now, let's take another example of regular expression which we can convert to NFA, given, if you can recall, the formula that we have gone through earlier. So you have the start state 0. First, you make the epsilon move. And here the regular expression, because it has A or B star, so we make another epsilon move from 1 to 2 and 4, which can accept A or B. And again, we make epsilon move to 6. And because it's a star, we go back from 6 to the previous, like the same, 1, because then it will remain to A or B. So this is based on the formula of the Klein star here that we have shown. And then from 6, we make another epsilon move because it's a NFA. NFA has epsilon moves. Then the end strings that it has is A, B, B. So we just make the state that it accepts A, B, and B, and then it reaches the accept state. So this is the example of the NFA that we can create from the regular expression A or B star A, B, B. And the DFA for that is that, again, remember, we have to start from the start state, and then we have to consolidate any of these states together to make the transition more compact. So Here, the way we do it, let's say in the DFA, we call the start state as A instead. So we consolidate the moves 0, 1, 2, 4, and 7 from the NFA to make that happen. And the same way we do that for this state B, C, D, and E in the DFA by consolidating the states from the NFA so that like it doesn't have any epsilon move and it doesn't have multiple state for the same input. So we have someone mention something in the chat. Okay, again, what is S's silent move? So when you say silent move, what do you mean by that? So it doesn't actually have silent move. It has epsilon moves, which means it just like has no input. It changes the state and it doesn't have any, how to say, input. So in NFA, when we, let's say, first create the NFA from the regular expression, we by default just put epsilon move, which means there is no input at all. Yes, Andre, Dragos, you guys are correct. So technically, we do not call it as a silent move, but like the technical term is epsilon move. So as you can see here, right? So from state 0 to 1, technically it has changed state, but there was no input, which is the epsilon. And the reason we do it is because NFA is sometimes easier to create because it kind of lays out the graph that is easier to understand that, okay, what should be our next transition. So we just use the epsilon move like just to denote in that way, if that makes sense. Now, after we have generated the DFA again is this one, which you can see it's a far more compact, like finite automata for the regular expression, which is this one. So after we have created the DFA, using this, we can actually generate state transition table. And that will be important because using state transition table, you can then determine whether like what is a token, what is an acceptable token or not. So once we have the DFA, it is easy to translate that into a table driven algorithm to recognize tokens. Each row corresponds to a state and each column corresponds to an input in this state transition table. And each cell tells us which state to move to for a given input in a given state. Let's take an example here. So let's say if we have the DFA like this, like consists of state S1, S2, and S3, you can see we can create a state transition table where on the row left hand side we have all the state that can happen, S1, S2, S3. And then the column is specifically to see because the transition can happen for 0 or 1. So we put them as 0 and 1. And now given this, so you can see S1 for 0, it can move to S2. So we write down S2 here. If the input is 1 for S1, it can move to S3. We write S3 here. And for S2, if the state is S2 and the input is 0, then it can it will stay in the same state, which is S2. So we write S2 in the state transition table here. And for 1, it moves to S3. So we write S3 here in the state transition table. And we traverse the different state again the same way for S3 as well. And we create the state transition table because this will now determine that given an input string consisting of 0 and 1, whether they will be accepted as token or not. Now we have someone post something uh, in the chat. Okay, let's take a break. My brain is dying after 3 hours of non-stop lecture. Okay, Andre, I really appreciate that. By the way, we are actually very near to the end of the lecture. So we will be wrapping up the lecture very soon. You do not have to worry about brain dead. Now, Dragos has mentioned, Andre, epsilon is basically a transition you only see in NFAs. Yes, that is correct. Like Somdip said, it's the lack of input that can generate a transition. That is also correct. That along with multiple possible transitions on the same input is what means a finite automata, non-deterministic. Absolutely, Dragos, you're correct in this sense. Now, we only have 3 sides left. So Kanya has pointed out, yes, that is correct. So we are almost close to the end of the lecture. So do not worry about being brain dead anyhow. But one thing, going back to the lecture, I want to point out. So given any DFA, you can see you can generate the state transition table. The state transition table will actually help you to kind of see which state can move to which other state based on which input. And that is important because let's say if your tokens, for this example, if your token consists of 0 and 1, you can determine which particular token can be accepted by this finite like DFA machine or not. If it is not accepted, then we do not consider that as a token. But if it is accepted, then that is a valid token or legal token for this particular DFA. So that's why we need to learn, like understand the importance of state transition table from DFA to generate tokens. Now, okay. So few other considerations that we have to keep in mind, that to save space at the expense of the speed, it may not always be appropriate to produce the full DFA, because DFA can also be complicated for some particular cases, and it might hinder the speed of execution. The lexical analysis needs to indicate the tokens found and any semantic information. So the reason we do the DFA is because from the DFA, we can generate the state transition table, which makes it easier to understand that which token is valid or not, or which token is found. And from there, you also determine the semantic information of the token as well. Now, all these steps and optimization are automatically done by tools. And by tool, I mean Antler. So if you can remember from our lab sessions, when we generate the, so we produce the grammar file, and then using Antler, we auto-generate the parse tree, and we can do further processing on that by using listener or visitor. But we never see NFA and DFA in practice. It's because tools like Antler automatically does this in the background. But the reason we are learning this is because NFA, DFA, or like finite automata forms the foundation or the theory behind how a tool like Antler is generating the parse trees. So how a tool like Antler is creating the tokens and then generating the parse tree from there. So in practice, we might not have to worry about knowing NFA and DFA, but in theory, it's very important to understand the concept of finite automata, especially NFA and DFA. Now, these are few exercises which like on your own, you can try them out, that if you have the regular expression like this, how to convert uh, to an NFA, and how you can then convert NFA to DFA. So, and you can also generate the state transition table from that. So these are some of the exercises that you might want to do on your own. And that being said, after you have done this, I have also provided a Python code which actually creates the NFA and DFA. So after, for this exercise, after you have created them on your own, you can write this Python code and try it out to see if the NFA and DFA that you have created is valid or not, or the state transition table that you create from the DFA of the example is valid or not. So that being said, we have reached the end of today's lecture. Let me stop recording and also pause the recording.